Okay, here's our video on the greenhouse effect. And when people first hear it, they might say, wow, well, that's a negative word, right? Greenhouse, global warming. Well, the greenhouse effect can have a negative connotation. It can be bad if it's a runaway greenhouse effect, which we'll talk about. Let's get our pen going over here. If it's a runaway greenhouse effect, now that's a problem. And we'll talk about that. So basically, what it is a blanket of gases like CO2, and there's also methane, and they're in our atmosphere, in the troposphere, the first layer of our atmosphere, the troposphere, which goes about maybe 7 miles up before you hit the stratosphere. So you think of it as a blanket of, and there's others, there's water vapor, a blanket that keeps us comfortable. So let's look at the temperature differences. So right now, the average temperature on Earth, and this is the average right now, is about 33 degrees Celsius, which is about 59 degrees Fahrenheit. That's the average. Well, obviously, it gets a lot hotter in the summer and a lot colder in the winter. Without, there's our little without the greenhouse effect, without this, the temperatures would be 0 degrees, the average, 0 degrees Fahrenheit, which is about negative 17 degrees Celsius. So it would be much colder. And if you want to get a little more uh, perspective on that, let's say in July in New York, right? In July in New York, you can get temperatures like 80, to 90 degrees. And, you get 100 degrees too. So without the greenhouse effect in July, and this is Fahrenheit. So in July, the average might be like 30 degrees Fahrenheit. It'd be cold in July. Right? And if you want to know in Celsius, if you're somewhere around the world, it's about 1.1 degrees Celsius. So imagine if it's without the greenhouse effect in July, how cold it would be. Imagine the other months. Imagine December. December in New York, anyway, can get 20 to 30 degrees Fahrenheit. You're talking minus 20 degrees Fahrenheit. So it wouldn't be too comfortable if we didn't have this greenhouse effect. So again, the greenhouse effect makes us comfortable. But a runaway greenhouse effect, which we'll also talk about, can be trouble. And this runaway greenhouse effect happened on Venus. So let's talk about that. Well, before I show Venus, let me just show you the atmosphere. And of course, this is an oversimplification because obviously there's more layers of the atmosphere. We're not just talking about the atmosphere, we're talking about the troposphere, which is the one we live in. Troposphere. There we have it. And you can see these are the greenhouse gases. This is CO2, carbon dioxide. Here we have methane, which we'll talk about. This is nitrous oxide. Now, you can't really see it there. Let me put it in there. There it is. There's also water vapor in the air. So you can see as the sun's light energy comes in, the solar radiation from the sun comes in and it hits the earth and it's going to be absorbed and it radiates out. And you can see that in a normal greenhouse effect that keeps us comfortable, a lot of the heat escapes and some stays, keeps us comfortable. With a runaway greenhouse effect, and I don't want to really say human enhanced because I'm not. This is not a video on global warming, but in an enhanced greenhouse effect, a runaway, we call it a runaway greenhouse effect, which happened on Venus. You can see that less heat is escaping, right, and more is being kept in. So that's basically it. So the more CO2, the more methane in the atmosphere, the more nitrous oxide, the more water vapor in our atmosphere, you get more of this blanket that's keeping the heat in, more heat in, less heat out. Think of it that way. So let's look at Venus. And here's our sister planet Venus. And it's almost the size of Earth. It's smaller than Earth. It's almost the size, right? It's the second planet to the sun. But it is the hottest planet in the solar system. And it gets temperatures of 800 degrees Fahrenheit. Extremely hot there. And it's hot because of the CO2, carbon dioxide, in its atmosphere. So it has 96.5%. Its atmosphere is 96.5% carbon dioxide. Where on Earth, here's Earth's percentages. It's 0.04%. So imagine if we had that, how hot Earth would become. So because of this carbon dioxide in the atmosphere, it's hot. It's extremely hot. It also has enough pressure on it. So Venus, and let's use let's use black. Why not? So Venus's pressure is 95 times that of Earth. 95 times. So if you landed on Venus, not only would you burn up because of the heat, but you would be crushed. Right? The pressure is too intense for us. 95 times that of Earth, and they call that 95 bars. Right? You might hear 95 bars. That just means it's 95 times greater than Earth's pressure. So the pressure is immense. Now, if you think about Earth's atmosphere, let's write that down also. Let's keep black. Why not? So if we have Earth's atmosphere, right, it's 78% nitrogen. 78%. 21% oxygen. This is the amount we want. We don't want any more or less. And it's about 0.9% argon. And the rest is CO2, that very small percent, and the methane we talked about, and the water vapor, and the nitrous oxide. So a long time ago, maybe billions of years ago, scientists thought that Venus had oceans. Maybe 2 billion years ago, maybe more. So here's Venus as it could have been in the past, and here it is now, this hellish place on Earth. And, with the Pioneer missions in the 80s, scientists have figured out that it did have oceans. It could have had oceans, right? There's a big question mark here we'll put for that. We'll use our yellow. It may have had oceans in the past. And where did all that water vapor go? Well, it disappeared. And because of that disappearance of the water vapor, CO2 would have built up in the atmosphere. So we don't want this to happen to Earth. And the Russians, they sent a probe, the Venera 8, or we say the Venus 8, the Venera 8. The Venera 8. It landed successfully on the planet, but it only lasted about maybe 50 minutes or more. Because of the extreme conditions on that planet, it just stopped working and it was crushed. So I'll show you a picture of that. And here's an artist's rendition of the Venera 8. Write it again up there. Let's use a different color. Use a different color. The Venera 8. Right? Or the Venus 8, whatever you want to call it. So it didn't last long. And you can see this hellish type of world that Venus is. Okay, now let's go back to these global warming or the greenhouse effect, how it's caused. Now, again, this is not a video on global warming. Not saying who's doing global warming, just showing about the greenhouse effect and a runaway greenhouse effect. And by the way, here is a actual picture of the Venera 8 that landed in 1972 on Venus. All right, so in chemistry class, we'll talk about fossil fuels. And these are the ones that will give us the coal and petroleum that provide us with energy that we need so far in our world today. And we're trying to get away from coal and petroleum because there's other sources like nuclear, which is the most efficient, solar, hydroelectric, and so forth. But if we look at these fossil fuels, one thing we should clear up right away is that the fossil fuels are not from dinosaurs. Right? We think of fossils, we think, oh, dinosaurs. No, the majority of fossil fuels come from bacteria. Write it over here. It comes from plants and algae, right? And we're talking about bacteria, plants, and algae that lived in the Paleozoic era, in this era, and especially around this time, the Devonian, say that 3 times, Devonian period. So we're looking at 410 million years ago. That's given us our coal and our oil that run the world right now. And when they burn, they produce CO2. Right there. There it is. And since about 100,000 years ago, CO2 levels have increased about 15%. But it's still only 0.04% of our atmosphere. And we could see, you may be saying, well, we are getting warmer. What if it was 1%? So even that tiny amount could change things. But it's not just CO2 in the atmosphere. Remember, I also told you there was also methane. And methane, and let's get a clear page on that. Oh, and by the way, showing you a picture of the United States in 1620, around that time. And in black, it's all the forests of in the United States. And of course, we know that trees absorb CO2. Trees and plants absorb CO2. So a decrease in forests, especially the rainforests in the Amazon, could lead to more CO2 concentrations in the air. And there was an old saying a long time ago. Now let's change the pen. That in around the 1620s, even during the time of Washington in the 1700s, a squirrel can come from right here, can go from Maine to Florida without touching the ground, just jumping over trees. Wouldn't be able to do that today. Just look at the forest in 1620 when the Puritans are coming over, right? People in Jamestown are already there, around over here, right? Jamestown. And of course, the Spanish were in Florida before that. So here's 1620, right? And here's 1926. So you can see the difference in our forests. And again, trees absorb CO2. So the lack of trees could have something to do with the increased CO2 levels. Now, I did say methane is also the culprit. So let's look at methane. So methane is a carbon, and these are basically the percentages. We have 79% of the greenhouse emissions are carbon dioxide, CO2. Methane is 11%, nitrous oxide 7%, and the other gases 3%. Now let's go back to methane. So methane is, like I said, it's carbon with 4 hydrogen atoms, right? That's methane. And methane, believe it or not, is 80 times more powerful. Well, I shouldn't say more powerful. It has 80 times the warming power. The warming power of CO2, carbon dioxide. In the short run, for the first 20 years, methane would be much more dangerous. And the culprit is agriculture, right? It's from the manure in the livestock. It's also, and here's a fancy word, the gastroenteric. It's a polite word for farts and burps. The gastroenteric releases. It's a nice polite word to say when you accidentally burp at the table, right? So agriculture is the main culprit for methane. So let's review what we learned today. In our atmosphere, and specifically in the troposphere, the one we live in the troposphere. Planes fly in the stratosphere. So in this area, we have our CO2, carbon dioxide. Of course, we have our nitrogen and oxygen, but the greenhouse gases that we talked about is CO2, carbon dioxide. We also talked about methane in the atmosphere, CO2 coming from the burning of fossil fuels, which we said are not from dinosaurs, but from bacteria and plants and algae that lived about 400 million years ago. And so we have our CO2. We also have our nitrous oxide and water vapor. And we know that this makes a little blanket that keeps us comfortable. Unless there's too much of this in the air or there is a runaway effect, which happened on Venus. And going by this pie chart again, carbon dioxide makes up the most of our greenhouse emissions. But methane, in the short term, could be much more dangerous. It's 80 times the warming power. Now, again, this is just all this together. Remember, nitrogen is the majority of it in our atmosphere, but all this together is a very, very small percentage. Remember, it's of the greenhouse gases, right? And in a natural greenhouse effect, let's get our pen going here. Well, use green. You can see the solar radiation coming from the sun, the light energy. It gets absorbed by Earth and it radiates as infrared. Electromagnetic energy radiates out. And you can see in a normal effect, a lot escapes into space and we get just the amount we need. But in a runaway greenhouse effect, less heat is escaping, more is being kept in because of carbon dioxide, because of methane, because of nitric oxide and water vapor. So if we that is really what a greenhouse effect is and what a runaway greenhouse effect is.